Well, welcome everybody. Let's get started. It's a pleasure to have Professor Kang Kuen from Harvard joining us today. Kang Kuen received her bachelor's degree from UC Santa Barbara and did her PhD work in Boulder with Debbie Jin and Junyi, where she worked on what was really one of a big landmark experiment in AMO physics, where she led the creation of the first ultracold gas of molecules at high density, which is now, it's a very active area of research. It's essentially a subfield of AMO physics that she really did the pioneering work in. After Boulder, she came here and did a postdoc with Jeff Kimball in this very building. And then she went to Harvard to start her own group. I had the honor of working in Kang Kuen's group as a postdoc, and it's been really fun when the group was just getting started. So it's been really fun watching a lot of these ideas, which not too long ago seemed kind of fantastical. You know, I think like this type of title maybe would have made sense for like a theory talk not that long ago, but now these things are actually happening thanks to a lot of really innovative platforms that Kang Kuen has developed. Her group works at the intersection of quantum information, quantum simulation, and quantum chemistry using ultracold controlled atoms and molecules. And the research you'll hear about today is something that really is at the intersection of all of those. In her group, they've built up the capabilities to control molecular reactions and interactions down to the completely quantum level. And so I'm excited to hear about what they've been up to recently. Kang Kuen's research has been recognized with a lot of awards and prizes, including the Demock Thesis Prize, Sloan and Packard Fellowships, a number of Young Investigator Awards, and the II Rabi Prize. So please join me in welcoming Kang Kuen.
Thank you, Nick, for that generous introductions. It's always a great pleasure to be back at Caltech. I actually came here first time when I was a little kid. My father had gotten his PhD, was Keystone long ago before I was born. And we visited many times later for his work. And I remember waiting sort of impatiently for him on the bridge by the library. And now actually I'm doing the same with my daughter who's here, but I was hoping that she would actually come to my talk, but we decided 45 minutes plus question is too long. So she's waiting out there, but I think she entertained herself better. So I changed my talk title a little bit from what was advertised to focus more on the story on the left here, where we want to discuss sort of the exploration that we've done for the roles of nuclear spins, quantum coherence, and entanglement in ultracold chemistry. And I think this is really some very new ideas, new capability that that we didn't think about that we could have, only like, a couple years ago. So I wanted to focus on that. If the time permits, I also want to tell you, highlight a little bit of the result on the right where we can control individual molecules, and this is actually the experiment that Nick joined to really help me launch. Individual molecule assembling from individual atoms to control all degrees of freedom, including their interactions, so that we can actually demonstrate and have demonstrated a quantum logic gates between two trapped molecules. Okay, so let me briefly say that nuclear spin is usually not participating in chemistry in the sense that it's a well-isolated degrees of freedom that allow us to report on chemical content of samples, for example, nuclear magnetic resonance imaging, where we can identify where water is by looking at where hydrogen is, or as magnetic field sensors for small scale. But it hasn't really been examined detailed to concern quantum phases, and that's what we want to investigate. So that's what I will tell you mostly about. But before that, let me just dedicate today's colloquium to Jeff, my postdoctoral advisor, whose good taste in physics and his critical mind had helped me tremendously as a scientist. I also had the fond memory of going on several mountain bike rides with Jeff. And here is actually one picture after we rode the Santa Monica Mountains. And here is in that same day, that's actually what the trail looks like. So I have really fond memory of that. His presence here is greatly missed, of course. Okay, so let me focus on, start with some very general introductions. Now we are at 100 years of quantum mechanics, Schrodinger's equation, so 100 years of quantum molecular physics and chemistry. Here I borrow a hand-drawn sort of record from Professor Dudley Hirschbach's Nobel Prize lecturer who got a Nobel Prize in chemistry in 1986, who is currently at an esteemed colleague in my department, in the chemistry department at Harvard. And here it was really about sort of probing intrinsic property of atoms and molecule in isolation, get a lot of the quantum effects. For example, the invention starting with molecular rays, so just molecule extracting out of a beam. One can make, heart shapes, for example, shadows, just really like a being of molecule. That's really the starting point. And Ultracold was able to use that to measure the Maxwell-Boltzmann distribution. That hasn't really been examined at this kind of level before to measure these velocity distribution. And then, of course, everyone knows about the Stern-Gerlach experiment that was attributed for the discovering of the electron spin, where one can, in the inhomogeneous magnetic field, separate the silver atoms into two spots, spin up and spin down. And Ultracold actually did a lot of really amazing, pioneering experiments since that time, one after the other. One was the electron spin, and then he was looking at interesting to look at the proton spin or the proton magnetic moment, and also the nuclear magnetic moment. So he actually used these type of experiment to measure the proton spin, for example, or the proton magnetic gyromagnetic ratio. And he used actually molecules for that because the electron spin is too large compared to nuclear spins in terms of the magnetic moment. And that's why you use a molecule where the electrons are paired up already, then you wouldn't have an effect from the electron and only the nucleus, the protons, for example. And he was using H2, HD, these kinds of isotopologue to measure, sort of the precision measurement to measure the proton magnetic moment, and found that it actually deviated what was expected at the time. And now, of course, that later attributed to the structure of the proton, which is the quarks. Quarks. Yeah, so that was, the experiment. Follow up from the Stern-Gerlach experiment. And then later, actually, Robbie, who was a postdoc with Stern, learned all these techniques, but invented another one. Instead of a static separation of two spins, he used a resonant magnetic resonance method to drive transition in actually atom and molecule. And in his first experiment that demonstrated the magnetic resonance transition was actually done with a molecule, again, because they're trying to make the nuclear magnetic moment measurement very accurately, and one needs a molecule that where the electrons are already paired up to be able to not have the electron effect, only looking at the nuclear effect, and demonstrated the, basically the Rabi. They didn't have the Rabi oscillation, but basically it's the essence of Rabi oscillation. Later on, Ramsey, who was the postdoc of, who was a student of Rabi, wanted to improve that technique further. And then, so he basically invented the separated oscillatory field method. So a Rabi pulse is split into two. So instead of a pi pulse driving from one transition to the other, he does the pi over 2 pulse and then wait for a certain amount of time to capture the phase difference between the oscillator and the the characteristic transition frequency to make a better measurements beyond what was possible with the Rabi technique. And then, of course, the invention of the maser, which I'm going to go into detail, sort of follow after that. This, I told you, this picture was taken from Dudley Hirschbach's Nobel Prize lecture. He was a student in the class of Ramsey at Harvard. He heard about the molecular beam techniques. He decided to use two molecular beam across molecular beam geometry to study collision of molecule, to study single collision chemistry, to really tease out the elementary step of chemical reaction, as opposed to in a solution or in a beaker where several collisions could happen and it's hard to tease out the individual events. So that was actually sort of the beginning of a lot of the gas-based physical chemistry work. And in sort of the more, so that's when chemistry and physics sort of start to split. Physics go more into control of atoms, some of molecule, I'll tell you in a bit, and then physical chemistry continue more on, investigating the different degrees of freedom or things related to chemical reactions with these kind of starting with the same kind of technique, but starts to split in terms of the scientific directions. So I talk a lot about molecule. Let me just briefly say that there are many quantum degrees of freedom in molecule. There is vibration, which can be used, for example, Raman imaging to get the molecular specificity of a content. These are two images of the same thing. One is optical field, the other one is Raman imaging, and you can see you're looking at the same thing, but here there is bad stuff, right? And you couldn't have tell from optical imaging. There is electronic transition, there's rotation transition, there's a nuclear spin, nuclear hyperfine levels. Here's just an example of MRI imaging of where water is in a cup of corn. And these are all sort of fingerprints of a molecule that we can identify using their quantum degrees of freedom. One more thing is one can also, there is another degrees of freedom, which is the motional degrees of freedom, and people have used gratings and throw vitamin, as large molecule as large as vitamin, through the grating to see these sort of double slit or multi-slit experiment. So these are sort of the quantum degrees of freedom that we have in a molecule. So what I told you about this sort of 100 years progression, right around sort of Ramsey invention and things like that, these techniques, there was the first atomic clock, which was actually based on the vibration of a molecule. This was the first time that we are able to keep time without referencing to celestial body motion, but only sort of the ticking of using the tick of a transition frequency of a molecule. And here, but hard to see. At the time it was the first, but it was by now the standard was the loose only 1 second in 300 years. But this by now is widely inaccurate. We wouldn't lose a second with the best clock for the edge of the universe now. So what is the ticking of the atomic clock? The atomic clock is really based on superposition of transitions. For example, S&P from your freshman physics or chemistry class, we make a superposition of that, and what you're seeing, of course, slow down by 10 to the 15 times. Ticking of the clock is how the density of the electron is modulating and in this sense. So a lot of the techniques that was developed in needs of making better and better atomic clock for precision kind of measurement allow us to beginning to control atoms and molecules more and more, including the invention of the laser cooling of atom techniques that we are now sort of the workhorse for a lot of the ultracold atom and molecule experiment. So atomic physics has gone through a period where we control everything about atom more and more. And now we're using those techniques to, again, coming back. I told you at the beginning, there was a lot of molecular work because of the quantum degrees of freedom, because of good reason that we want to choose molecule versus atom. But afterwards, there's a lot of work that was done in controlling atom, which is simpler, and now we're applying those techniques to molecules. Okay, so some of these sort of references that I put up here, which is at the turn of 2000, was recognizing that molecule actually, these intrinsic property of molecules are very good for tests for example, time reversal symmetry with molecules. Some of the work that Nick is working on in different sectors, electron and hadronic sectors that utilizing molecule, recognizing that, and also thinking about quantum computation with trapped molecules. But of course, these ideas seem to be, at the time, seems to be very far away. But nowadays, we finally start to get more control and beginning to, we have now measurements, we as a whole community have measurement using molecule to push these measurement sort of 3 or so more order magnitude better than what we can achieve with atoms. And on the right-hand side, we now have the quantum logic gate with trapped molecule. So my group focused on our work on sort of the scientific direction on the right-hand side here. People pursuing ultracold molecule for a wide variety of reasons. Nick is pursuing very much in the search for new physics. We are using some of the similar techniques for direction in studying quantum phases, quantum computation, and ultracold opportunity ultracold chemistry. Okay, so let me just focus on this topic first. This is going to be the main part of my talk, and if there's time allow, I'll tell you a little bit about the quantum logic gate with the molecules. Okay, so we want to ask the question of, can we harness chemical reaction for quantum science? And I want to ask a more specific question, which is, in a chemical reaction, we have two molecules, and very simply drawn as a diatomic molecule, colliding to form products. The question is, are these products ultimately entangled? Okay, this is a very grand question, and I want to ask something a little bit more specific, which is this ask, when can phase coherence be maintained throughout a reactions? If so, can we leverage it to generate entangled product? Meaning, if we can have some kind of entanglement here to initially we can prepare it. And if the phase is maintained throughout such a reactions, then maybe the product will be entangled because the phase is unchanged. Okay, so that's the idea. You prepare entangled spin within each molecule, then use chemical reaction to break up the initial molecule into separate entangled molecules. Okay, so what do we need to start examine such a question? We need molecule in a single quantum state so that we know we're preparing in the entangled state, for example. We want a chemical reaction so we can break up these atom pairs into, two separate ones, two new products. And we need to detect the state of the product so that we know what happened to the state. And not only detecting the state, we need to detect those states in a coincident manner, because we need to know that they come from a single event. So any quantum correlation can be teased out. Things in the average sense will not show these very fragile quantum correlation. Of course, one can imagine we probably want to avoid anything chaotic, because if everything chaotic, it probably means phase is washed out and we won't have any unusual correlation. So we want to avoid such we want to avoid such dynamic, and then we want to see whether coherence survive after the reactions. Okay, so to do that, let me just go through this checklist and tell you the story of where we are. So molecule in a single quantum state. Nick had already mentioned this experiment that I did together with so-called opticals in the group of Jun Yi and Debbie Jin in 2008. where we were able to prepare a gas of molecule in a single and the lowest hyperfine rotation vibration electronic constant. So all the quantum degrees of freedom of a molecule, we can prepare them in the lowest one. If I had time, I'll tell you how we make it in the second part. But if not, then just take this as a starting point that we can make molecule in a single quantum state. Okay, and we can take absorption imaging like this to know how many atoms, how many molecules, and what's the temperature of such a gas. Okay, so once we made this, and then of course a number of lab around the world nowadays can also do that. Once we made this, what we found was that these molecules as a function of time, which we hold in our vacuum chamber, actually goes away in pairs. There's a two-body loss at a time scale faster than the vacuum lifetime. So something is happening to it. We didn't really know what it is, and we had a guess, but we couldn't really verify the guess until we actually have a way to see what happened. And this is when I started my lab in the other project. That's not what Nick worked on. In my lab, we decided to combine tools from chemistry and physics to really examine what happened to that loss. And this is combining the AMO techniques, which is the technique which I didn't elaborate, but we can prepare molecule in a single quantum state with physical chemistry techniques to probe the reaction. This is actually what the lab looks like. So it's definitely dangling wires and optics are everywhere. Not like a chemistry lab, but very much of the complexity is there so that we can study something conceptually very simple. Okay, so the tools that we introduced, apart from these absorption imaging that you saw on the cloud, gas of a molecular cloud, is that we can have our gas of molecule prepared here, or atom molecule prepared in the vacuum, embedded between electrodes, and zap it with UV light to ionize this gas. And depends on the time it takes to arrive at the detector, we have basically a mass spec to resolve to identify the species due to sort of the mass spectrometry. Okay, so that's one information. We can also actually, in fact, we designed these electrodes in such a way, this is borrowing techniques from physical chemistry, such that we can map the kinetic energy of this gas into rings, so this way we can also know something about the momentum or the kinetic energy of that gas or whatever comes out of that gas or after the reaction or so on and so forth. So with these tools built, we were able to see the reason of the two-body loss was indeed happened due to a chemical reactions. And this chemical reaction was two KRB molecules goes to the product of K2 and RB2. It does go through a long-lived intermediate complex stage where the four atoms come together and live for, actually we measure to be, we have a means to measure to be about 300 nanoseconds. Okay, so now we have a molecule in the single quantum state, we have a chemical reaction. Our next checklist is to detect the state of the products. For this, we use a spectroscopy technique where we can drive a transition of the products through a continuous wave laser, and then we subsequently ionize whatever is up here with another pulse laser. This is actually sufficient because our chemical reaction releases very little energy from the standpoint of chemistry, so 10 Kelvin worth or 10 wave number worth of energy, which is insufficient to excite vibration, only rotations. So we only need to resolve the rotation quantum number of the products to tell us what the products, what quantum state we have there. Okay, so this is our technique. And to do coincident detections where we can identify single collision events, we do these quantum state ionization for both potassium dimer or rubidium dimer simultaneously, and then have it come to the detector, okay? And once it comes to detector, we record, the number of events, and we actually also filter using the momentum conservation constraint. So if chemical reaction happen, which is basically at ultra-cold regime, the velocity, the kinetic energy is very, very negligible. So essentially, there is no momentum, total momentum, you can say it's zero, or velocity is zero. But after a chemical reaction, it takes 10 Kelvin worth of energy, partition into rotation and kinetic energy. So the two products has to have equal and opposite momentum, and that's quite large, but the sum of that is equal to the initial condition, which is zero, which means that we can constrain our counts to these momentum conservation because we have a way to detect the momentum in both X, Y, and Z direction. So for example, if we're looking for a particular channel, these are all the counts that register for those particular reaction channel product. And then if we apply these criteria, we end up with the events that you can kind of see that if we draw a point from red to blue, they're all kind of origin from the center. So this way we can identify pairs that comes from a single chemical reaction event. Okay, so this is crucial to tease out the unusual quantum correlation. Okay, so actually with this tool, one of the first things that we did was to test the fact that the chemical reaction actually goes through a very long-lived complex stage, and therefore one expects that the product to be a statistical outcome in the sense that every possible quantum channel are equally likely to be occupied. And this is what we did to show that there's actually 57 possibility in 57 possible rotation state pairs. So potassium dimerine, these are possibility. Rubidium dimerine, these possibility. There is actually one quantum degrees of freedom we're not measuring, which is, there's a rotation quantum degrees of freedom. That's 2 vector. There is also when the two molecules separate, there is an orbital angular momentum. So that's a third vectors. When you have 3 vectors added together, there's many different ways that they can add it to 1. One is the initial quantum number from all these possibility, and we only measure 2 of them. So the third one is a degeneracy factor. So that's why the heights are different. And for channels that are similar in quantum numbers, will have more ways of making, add it up with a third vector into 1. Okay, so this is why there's more possibility, more degeneracy here, which is reflected in this measurement. Okay, so with this sort of precise measurement, we can compare our directly to the counting statistical model. And you can see that most of them actually explained very well by the statistical model, but there are actually 50 pairs match the expectation, but 7 pairs deviate from the statistical expectation. I mean, the point here is actually to say the distribution is mostly statistical, indicating a chaotic dynamic, but we have a means to tease out the channel that are not, but we don't have the theory to tell us why they're not, because the theory is beyond the state of the art. This is too complicated with 4 heavy atoms to calculate beyond statistical model. Okay, but the point here is that it is mostly statistical, so mostly chaotic in the rotation degrees of freedom. So this is probably not where we want to look if we want to look for coherence and entanglement and things like that, okay? So we have all the tools built that, but we want to avoid chaotic dynamic, and therefore, instead of looking at the rotation degrees of freedom, we want to look elsewhere, and that's the nuclear spin degrees of freedom. So let's look at the nuclear spin degrees of freedom, which I haven't spoke about. The molecules that we prepare are initially in a well-defined nuclear spins. That's just in the prepared molecule in the single quantum state. That's given when we prepare them. We don't actually measure the nuclear spins because they are spectroscopically, they are too minute to discern the different energy levels. But because the products are homonuclear molecules, are indistinguishable, in some sense, indistinguishable nuclei, that these molecules has to respect the quantum exchange statistics. So if we have, potassium dimer, which the nuclei are bosonic, the exchange statistics has to be, symmetric, while the fermionic nuclei of rubidium dimer has to be antisymmetric. Okay, so that symmetric antisymmetric has to play. It has to be a product for both the nuclear spin part of the wave function as well as the orbital, the exchange part of the wave function, the orbital wave function, just like the electron spin, which is it has the spin and the orbital wave functions. These has to be respected also in the nuclear, also for the nuclei. So by measuring the even or oddness of the rotation of the molecule, we can know the symmetry of the nuclear spins. Okay, so either they're symmetric or they're antisymmetric. Those are what the things that we can tell. So if we start out in a well-defined state and nothing changes, the red line points down and afterwards it's still pointing down, then this is a symmetric scenario. We will end up with measuring the potassium dimer in the even rotation state only. Okay, and so is for the blue atoms. In that case, it will be the odd only. Okay, so this way we can tell something about the symmetry of the nuclear spin, even though we did not directly measure them. Okay, we can actually change these nuclear spin content by varying the magnetic field. So the probability of, in reality, we don't work with spin. These are not spin 1/2 system. They're really, higher spins. So we actually, as a function of magnetic field, we can prepare them in starting with a single one or a superposition of 3 different ones in the uncoupled basis. I'm just drawing them in different direction as a way of showing that they're in different, they have different projections that can be tuned with a magnetic field. And then one can predict based on that, nothing changed. The only thing is we swap the atoms, the spin projection is still in the same direction with the same, probability or phase. Then we can predict the symmetric and the antisymmetric proportion as a function of magnetic field. Okay, so long story short, these measurement follows very well to the prediction where nuclear spins are spectator in these reactions. Okay, a little caveat here is that this was measured without the coincident detections. So we were just looking at potassium in a particular channel and looking correspondingly rubidium in a particular channels as a function of magnetic field. Okay, so far we have constructed a very simple model of how the nuclear spin should behave. We check the population and see that the nuclear spin is indeed a spectator. Okay, but we haven't had a chance to really look at the phase information, which is what's needed to say something is entangled or not. We need the phase information to say something is entangled or not entangled. So the idea is the following. We prepare entangled spin within each molecule. So the rubidium and the red and the blue atoms can start with some kind of Bell state, up, plus down, for example. And they're identically prepared for foreign ensemble. And after a reaction, they exchange partner. And this blue atom used to be entangled with the red atoms. Now, after the reaction, they live in 2 different molecules. So the question is whether they are still entangled, like whether that entangle survives such a chemical reaction. Okay, that's a hard question to answer. So we want to start with a simpler one, which is, would the coherence be maintained throughout the reactions? First of all, just the phase is maintained. And if so, then it would already imply, although entanglement would be a much stronger set of measurement one will have to perform. But first, is the phase that we prepare, whether that will be maintained. So that's the question we want to answer. Okay, so let me walk you through a very simple model. This is a simple model to be tested, which is assume the coherence survive. The initial state that we have here, a little bit hard to see. The initial state that we have here, we're just going to assume we're spin 1/2. So up plus down down for A molecule, and up plus down down, identically prepared for B molecule, and that's just a tensor product. And after a chemical reaction, if I assume chemical reaction does nothing but swap the atoms. So first I multiply all the turns out, so I get 4 turns, and then I swap the atoms, so potassium is paired with potassium, rubidium is paired with rubidium, like this. All I'm doing is multiplying it out and put potassium on one side, rubidium on the other side. I had these 4 new terms. Okay, and what I found is that there is these terms and these terms which has a well-defined symmetry. In the middle, actually, because the indistinguishability of the atoms, we need to properly symmetrize this to be a total spin system, to write it in total spin, because we cannot say A is up, B is down, or A is down and B is up. It's really a combination of those to be properly symmetrized. And when I do that, I found that correspondingly to the even and odd of the rotation, that these actually destructively interfere. Okay, so now I'm left with the predictions that if coherence survive the reactions, I will have only even odd or odd even combination of the rotations measurement and no even and odd. Okay. Now, if we have incoherent, process where I don't worry about keeping track of the phase, then all of the possibility remains. There's no destructive interference, and therefore I would expect to see even, odd, even odd, even channels. So now we have a prediction based on a very simple model, and what we can do now is to check what we will get. Okay, so we will get 5 gauss where that's the place where we have strong nuclear spin-spin interaction, so we can prepare such an entangled state to begin with. We pick rotation pairs of even to be the 10 quantum number, ought to be 9 for purely detection purpose. We make the predictions of a fully coherent, just using this very simple model, fully coherent scenario would give us, depends on these coefficients we started out with. In our case, we will have 0.7 population in the even odd channel and 0.3 in the odd even channel. If we have fully incoherent, then we have all these possibilities also on the off diagonal. And you can see that if we have only potassium detection independent of rubidium detection, these things add to be 0.7. We could not tell the difference between coherent versus incoherent. This is the reason we need to tease out the individual event so we can actually tell the difference between the coherent prediction and the incoherent prediction. Okay, so maybe it's a time to pause at the moment. Who think we will get a coherent result? We'll measure coherence as the outcome of the reactions. If you think that, raise your hand. Half of the people. And who think it will be incoherent? Chemists, yeah, and okay, also left hand. So you guys have a lot of faith in the chemical reactions. So let's check. It's really an experiment that we didn't really know what to expect. We had a prediction, a simple model, and we see what happened. Okay, so what we have here is state pair, even or odd, which has large count, and odd even, which has large count. And actually, even odd have a small number of counts, but certainly match better to the coherent case. But we're experimentalists. We're like, why? This is trending toward coherent, but why is it not 0? We found that there's actually background counts because when we ionize for a particular channel, the single photon can ionize, with the 2 photon probability. So that's not a true count, it's just background count. And when we measure that, we can, subtract that out. And so this is actually what we measure, 0.7, almost 0.3, and the off diagonal are with the confidence integral pretty much close to 0. Okay, so this is the result in the bar graph. We measure pretty much matching the coherent predictions and not consistent with incoherent prediction. Okay, so coherent is consistent with one with a high level coherent Okay, so this is really not a result that we would know a priori, because we just don't know what could mess up. Like if you say everything is really as simple as presented, if a chemical reaction for this particular case really follows what I just said, then of course this is what we get, but a lot of things can come into the way, right? So I think those possibility was out there, and you'll see that actually both are possible, depends on the scenario. Okay, so we were actually very happy to see that, of course, because we now can check coherent that indeed survive, and this does imply products are entangled, but not rigorous shown, because we actually only make a phase measurement, we embed the phase info, so we only make a population measurement, the phase measurement is imprinting into the population. Okay, so open questions. Entangled products need to be rigorous shown via direct phase measurement, but we have only measured part. This is the point that I just made. But what would break the phase coherence? There are people who raise their hand about coherence will not persist, which is a valid prediction as well. So the question is, if that were to be the case, what would break it? And in fact, we are examining such a role of nucleus being at the level of quantum phases, and that could be a new way of scrutinizing these short-range physics that could not be done previously. Okay, of course, we're also on the flip side, we're very happy that we see coherence persist. The question is, is this general? What about reaction in, much hotter warmer temperature, not in gas, but liquid? I think this could be more general, because nucleus spin is indeed quite isolated from other degrees of freedom. So one can imagine, system with long nucleus spin coherence can show this. It's just that it's hard to prove without having the single event detection capability. But I believe that it's probably could be more general. Okay, so but then the next question is, now we have this nice result. How do we actually harness for some kind of quantum application? Okay, so before I go, I'm actually kind of running low on time. Let me just say that we have actually, for those people who raise their hands about the coherence not persist, you're also right, actually. So it turns out we had prepared different nucleus spin superposition initially, and this time, the previous time we prepared two, initial preparing the nucleus spin in a particular state, ran the magnetic field to a field where the nucleus spin-spin interaction is strong. So it's an eigenstate, an energy eigenstate. We can prepare a non-energy eigenstate by, doing that same thing. That would be our zero state, and then do a microwave transition to the rotation excited state and back down to prepare a superposition of two different nucleus spin state, still an entangled state, but not an energy eigenstate. And when we do that, we found, depends on what we actually prepare, the result is neither coherent nor incoherent or statistical mixture. And sometimes we have these measurements even above the statistical mixture prediction. So it's really actually very puzzling why this is the case. Okay, and something maybe very fundamental about, or something basically telling us about, something about that the energy eigenstates are, in some sense stationary state somehow throughout the reactions, and starting with the non-energy eigenstates, can easily break, in some sense, indistinguishability, but how exactly one breaks that, we don't really know. So this is an area that we're investigating. Especially wanted to investigating further using what we call the idea of a reaction interferometer. Okay, so I know in interferometer is a very a well-known techniques, especially developed here. The idea here we have is to ask the question, how do we measure and alter the phase? I mean, we're not actually measuring the phase at the end. We don't know how to do that yet, but maybe we can alter the phase initially and see what happened. And in our case, we have two arms of the interferometer. Our chemical reaction is our beam splitter to tell us the indistinguishability of the potassium dimer and the rubidium dimer. The idea is that we want to split the cloud into two, split the cloud, imprint a phase, relative phase between this arm and that arm in their nucleus beam superposition state, merge them back for beam splitter reaction, reaction serving as a beam splitter, and detect the products to see coincident detection, to see what happened. And we, in our simple model, fully coherent, if we were to do that and alter the phase of one of the arm as a function of this imprinted phase, we do expect to see on particular channel that we start with, these oscillation, even or odd even or odd even to come out. Okay, so there is possibility where we can, if there's an imparted phase, that it can go beyond what the initially naively statistical mixture can predict using the assumption that we have only zero imparted phase to begin with. Okay, so and this is an ongoing experiment that we're beginning to set up, where we are now basically splitting. This is just the beam splitting two optical beams to trap our molecules into two separate clouds, imprint the phase, and make an ultimate measurement. Okay, so I think I'm running low on time, so I'll just maybe in 5 minutes briefly give you a highlight of the second topic. Okay, so entangling physical system, I introduced these possibility of taking chemical reaction as a way where we use well-defined interactions initially in the state preparation and separate them into products and potentially maintaining entanglement, although we haven't shown that rigorously. Another way, which is more traditional or conventional, is to use a well-controlled interaction. Okay, and in this case, we are in our implementation is optical tweezer array of molecules with dipolar interaction between them that we can. So they never come close. They're just stay put about 2 microns apart, using their long-range interaction to tune exactly that, to entangle them and to demonstrate a quantum logic gate, and in our case, an I-swap gate. Okay, so let me just give you a motivation that I already spoke about. All the quantum degrees of molecules are much harder to work with because of these degrees of freedom, but we think they are really good for quantum, simulation or computation possibility because we can leverage them for complex degrees of freedom if we can control all of them to tailor to multiple requirements that we want for qubits, for storage, and for interacting when we want one capability to happen. And this interaction is due to the electric dipole interaction. Okay, but a prerequisite is to have more control, individual particle control, and control their interaction. And that's what we have been working on for the last, actually for this specific direction, 10 years. But overall, starting really from work that built up from when I was a graduate student. Okay, so without going into too much detail, We can control individual atoms. Actually, this is something I reported. Most of you were not here. Last time I was here for a colloquium in 2019. We have just gotten this result where we can, load individual atom, prepare them in the lowest quantum emotional states, merge them into the single trap, and with magnetic field and optical field to form molecule in the lowest vibration rotation. The single quantum state that I spoke to you about, these are sort of the breakdown of step, but with single particle resolution. Okay, so I'm not going to go into too much detail to skip ahead. So in order to entangle or to interact these molecules, we use the dipolar interaction, which can be mapped onto spin models. So in the rotation ground and excited state, which are these S and P orbitals, I show you these ticking of the clock, so basically two levels, they can interact at these characteristic frequency of 3.5 gigahertz. We can engineer a gate, which is to bring in a third energy level such that which initially are also in the S orbital, so no interaction effectively between the two qubits, but one can turn on and off the interaction by bringing into the manifold between S and P, like in this case, allow them to interact for a certain amount of time, bring it back down to the non-interacting manifold, and then complete the I swap gate. Okay, so this is an experiment that my former student Louis Picker worked on, who's now a postdoc in Manuel's group, where we chose exactly those three relevant levels, of course, out of a manifold of 32, or actually 100, actually both excited state and ground state, so 140 levels. We picked three levels, SR0, 1, and E. We engineer magic ellipticity trapping, so the optical tweezer need to have the same potential, so any fluctuation won't become a frequency difference of the energy level that are going to be resonantly interact, so we have to work on that. We develop multi-state readout so that we can, actually, let me just say multi-state readout, so we can discern molecule in different states, 0 and E, 0 and rotation excited state, such that we can throw away, in some sense, events where we didn't create molecule, because that turns out to be a big background. Okay, so we can read out molecule in rotation ground state, do a reverse molecular disassembling process, and then for molecule in a different rotation state, we first dissociate molecule in angle to 0, hide those ones, and then do it the same way. So this way we can do, a single shot Rabi oscillation between the two rotation states, and sequentially to figure out sort of the full state mapping. And if we don't see, then in 0 or 1, we throw that data away, so that that we don't mistake a no molecule event as the molecule in the state that looks dark. Okay, so this was important. Let me just say, with that, we are able to see dipolar interactions. So bring two molecules side by side, tuning their dipole-dipole interaction through the tuning of this elliptical polarization magic ellipticity in the laboratory frame. I won't get into the detail, happy to answer any questions. And prepare them in the Ramsey sequence, so pi over 2 pulse, waste some amount of time, pi over 2 pulse with a spin echo pulse in between, and see a coherent dipolar interaction between the two molecules. So these are what these oscillations demonstrate. Okay, so let me just say that if we wait exactly at this point, we can generate belt state. So if we just prepare it, with a pi over 2 pulse, wait 664 microsecond, molecules are in an entangled belt states, which we can check using techniques that are standard in atomic physics. So to measure both the parity projection, so both they need to be in 0, 0 EE, basically 50% of the time. We need to measure this phase of non-trivial phase factor of -I through parity oscillation measurement. Long story short is that we were able to entangle them with a fidelity of 94%. So we were happy with that, except for we know we can do better because we were hoping actually our very first number will already be has more nines than this first one. And we found the reason, again, without going into details, just to say we can completely model what happened to a pair of new measurements that's in collaboration with Anna Maria Ray and her postdoc to figure out that it turns out it's really the thermal motions of the molecule in the tweezer that are dominating the decoherence of this dipole-dipole interaction is depends sensitively on the separation of the molecule, and the thermal motion actually plays a big role. Okay, so we were able to characterize the molecule temperature through a pair of measurements, and with that, they were able to put in that particular measurement number into theoretical simulation and actually calculate these lines that match very well to our system. Okay, so with that, we know actually in the future, if we increase our ground state fraction, actually a moderate amount, okay, from this 34% to say 80%, and fixing actually there is astigmatism in our optical tweezer, we should be able to really approach many nines in terms of entangling fidelity. So we're very excited about that. Okay, so then the last thing is to actually show these gate, at least for this one paper, the demonstration. We encode the qubit in a pair of hyperfine states, so not just using those rotation states, which can be switched on and off the interaction by going into the rotation state through nuclear quadrupole coupling. So these are intrinsic coupling that we have in the molecule. And that gives us the total gate time just under 1 millisecond. We can, condition everything on detections, have a population truth table output very similar to what we expect from these entangling fidelity. But it turns out with state preparation, these transitions turns out to be quite hard. This quadrupole nuclear quadrupole coupling, actually is quite weak. So it's hard to drive and make a good state preparation. So if we actually don't condition on these detection in the right state ultimately, then that probability drops. Okay. So I guess the whole point is that we can, as a proof of principle, leverage the intrinsic property to give rise to highly coherent interaction. Quantum state preparation, though, still remains a key challenge. But this is a very different kind of challenge compared to other qubits, more of a state preparation issue and less of a 2-qubit sort of coherence issue. 2-qubit coherence issue is dominated by this thermal motion, which we can, which we can control. Okay, so with that, let me just put up the summary slide to say that the first part, I tell you, the main story where phase coherence is preserved in such a reaction, such an atom exchange reactions, actually kind of surprisingly, for the nuclear spins, but only for nuclear spin state prepared initially in an energy eigenstates. For the initial nuclear spin state in the non-energy eigenstate, preliminary data shows that nuclear spin actually might play a role, and how it plays a role, we don't really know. So more experiment is needed, and we're thinking about these atom reaction interferometry kind of experiment. Very quickly, I told you about our story about controlling single molecules, sodium and cesium, for its large dipole moment, that we can entangle them, we can demonstrate quantum logic gates, and we now understand the fidelity limitation due to thermal motion, so there's a path forward to improve that. And also we know we need to improve the state preparation of the molecule. Okay, with that, I wanted to give thanks to my group. Here are the actually large number of people, and many people have moved on from since this picture was taken. And a couple of them are in the audience. Both Nick and Luz have contributed tremendously to the work that I presented here. And with that, I thank you for your attention.
you have any questions from the audience?
Kang Kuen, great talk, of course. So one is a very fantastical question. So, I'm always amazed that you can make molecules just by bringing the atoms together. And, then you do all this work to characterize them so perfectly. But let's say your goal is not to keep perfect control of the final end product. To what extent can you just keep bringing atoms together to the same species and make bigger and bigger things in the trap?
Yeah, I think it's a question of efficiency and how well you know the spectroscopy, so in terms of feasibility. So I don't think it's a very scalable way. I mean, certainly people have shown that in principle, you could probably make two, you start with two, you can make 3 or 4, but it's not a very scalable way because you have to control individual atoms really well, and then that's usually controlling the motional state of the individual atoms, and that has deteriorated, over the generation of the experiment, for example. So it's like if you do ground state cooling 90% in one direction, 3 direction is already 70%, one species, and then the second species, another 70%, you're down to 50%, and then you keep multiplying that, you have very, very low. And that's just one step of the creation. A more general approach for cooling, bringing molecule down to lower temperature would be actually the approach that Nick is using, which is these laser cooling approach where you start with a metal atom and will stick onto the molecule you want and use the atoms to do the cooling of the motion, and ideally when you do photon cycling, not touching the rest of the molecule you care about. And that's a much more scalable approach in terms of going to bigger molecule to colder temperature. Yeah.
Can I ask a second follow up? So in the coherence experiment, the molecular reaction,
Yeah.
what was if you just take an isolated molecule, what's the lifetime of nuclear spin coherence in the isolated molecule compared to the reaction time?
Yeah, so I don't quite, but it's certainly on the order of seconds or 10 seconds. Yeah, so and the reaction time would be like collision time would be on the order of tens of milliseconds. The complex lifetime is on the order of hundreds of nanoseconds. So
there is a kind of implicit bias towards thinking that coherence will survive.
Right, exactly. But it turns out that in terms of even when I prepare a superposition of nuclear spin in the non-energy eigenstate, I still have these seconds of coherence time, but somehow these coherence product outcome is not there. So there's something that happens during the reaction and we don't know what it is. Yeah.
So just a follow-up question on this. So the spin and the rotations are tightly entangled because of the symmetry of the particles.
Yeah.
And then there's some sort of a selection rule for the spin, in coherence experiments at least. Does that then imply, when you look at the various rotation channels, the population of various rotation channels, it should be reflected in?
Yeah, that's a really good question. So the individual even channel of 2, 4, 6, and 8, we don't know. But what we know is even versus odd, or so it's a different metric. And it does imply that it may, and which is very surprising because the vibration, I mean, it's not vibration, rotation is a much more chaotic process. So we don't have a way, if we can directly measure the nuclear spin, it will be better. But it does imply that rotation might not be so chaotic. Yeah, exactly. Yeah, exactly. Yeah. So I mean, I guess the reason I think most physicists, I don't know, physicists or chemists, but people raise their hand that it will be coherent is partially also because we believe that, these processes, you can just write down such a simple equation. But in reality, the question is what breaks that, right? Like what interaction breaks that? What is the reality? Like maybe that is the underlying framework, but we have not had a way to check it before. And so therefore we cannot say it's right or wrong, but you know, it just, I mean, maybe that's not really that meaningful, but we had to check it to know. Otherwise, you know, I also talked to theorists that would just say, that's just gotta be the case, because that's how you will write it and treat it, and you can't think of other ways to do it. But we had, and you know, as experimentalists, had to check to really see these quantum correlation, yeah.
But you could compute the coupling between the relaxation is caused by coupling between the spin and the various degrees of freedom of the molecule, and it will be different and Sandeep has thought about this problem, and so one could predict, I think we could predict the change in coherence.
Right, but I think the question is exactly what the couplings are,
Yeah,
yeah.
that can be computed.
Right, but I guess the question is, what is the mechanism? Because right now, the reason the problem is the nuclear spin right now is quite isolated from other degrees of freedom is that electron spin doesn't really play a role. These are singlet molecules. The electron spins are paired up. But what is the difference between energy eigenstate versus non-energy eigenstates? You know, how do we describe then in the complex when we have 4 atoms? I guess I don't really, I mean, the answer I have is that we don't really know. And if you think we can compute it, I think it will be very interesting to see what is the term, you know, that contributes such a coupling, and maybe we can quantify it and
I don't know, I'm
And
guessing
make a
there's a
prediction.
spin rotation coupling matrix element that causes, that would be very different because the mass, the rotational state, in the moment of inertia is changing. But I don't know if that's.
But even qualitatively, I think it's hard to convince oneself that rotation is completely chaotic and the spin is completely achaotic.
right,
There's some
there's no
disagreement
correspondence
between those.
between, yeah, exactly.
There are no more questions. Let's thank our speaker again.